So, Chapter 4 is a bit of a standalone in first semester in particular, because we're not dealing with a specific like family of functions or type of function. So this is a little bit outside of the general layout for the course, but it's an important topic nonetheless, because again, it's a technique that's fairly common, and a lot of other kinds of problems turn into this kind of a problem. So just to give you guys a little bit of an overview, the setup for this chapter is going to be a little bit different. We're mostly just going to be talking about solving techniques. We're going to talk about graphing, substitution, elimination, and then we'll talk about some matrix methods. Most of us probably are not familiar with what I mean by a matrix, but that's okay. It has nothing to do with the movie by the same title. And then we're going to talk about some applications. So ways we can use these solving techniques to do other kinds of problems. So one of them specifically is going to be writing the standard form equation for a quadratic where we're given 3 points. One application will be area of a triangle, and I guess this is mostly like really more of a matrix application rather than a solving a systems application, and then we'll spend some time doing an array of story problems, because there are some fairly common-ish everyday situations where solving a system is really how you would answer that kind of a question. And this is basically what we're going to be focusing on here in Chapter 4. So we're going to start today talking about solving techniques. And that's kind of be where we'll spend really the first half of this chapter is going to be working on these solving techniques and practicing them. And then we'll start doing some applications where it's more than just like, here's the problem, now solve it, where you have to kind of be able to set the problem up a little bit for yourself also. But before we do that, really we need to talk about what we mean by a system of equations, right? So we say that a system of equations is a set of two or more equations that have to be true simultaneously. So what does the word simultaneous mean? Like at the same time, right? So usually when we write a system, we'll start with like a curly bracket. And it'll just be a one-sided curly bracket. just to show that these two, or the equations that we've written here, need to be taken kind of together, that they're all in the same system. So, for example, yes, Brady? Sure. This system, 2x plus y equals 5 and x minus y equals 10, has the solution 5, negative 5. Why is that a solution? Well, if I plug into, we'll say, call the first one equation A, and maybe we'll call the second one equation B. If I plug 5 in for x, and then negative 5 in for y, I get 10 minus 5 and that does indeed equal 5. And then also 5 minus a negative 5 equals 10. The same thing is true for equation B. So it's easy, it should be easy to check if a point or a tuple is a solution to our equation. All we need to do is plug in to all of the systems, or all the equations in our system, and make sure that all of them are satisfied by that. Is everybody okay with what we mean by a system of equations and a solution to a system of equations? Okay, good. So let's talk about the first technique to solve this. And that first technique we're going to talk about is called graphing. So I'm not going to write out any kind of formal instruction here. I'm just going to kind of look at an example, do an example, and kind of talk about what it is that we're doing. Because it's kind of hard sometimes to describe verbally what it is that we're doing. Oftentimes it'll work much better just kind of looking at an example. So what we're going to do is we're going to graph these two equations on the same axis. Okay with that plan? To graph something like this, it would be much easier to deal with if the y's were by themselves, so these look like slope-intercept equations. So I will, using the first equation, I'm just going to subtract 2x from both sides. And in the second equation, we're going to subtract x from both sides and then divide by negative 1. Everybody okay there? So if I wanted to graph these, how many points do I need to graph something like y equals negative 2x plus 5? What kind of a graph is this going to make? What shape? A line. How many points do I need to graph a line? 2 is enough. 3 would be fine, but we can do it with 2. Let's shoot for 2. Now, in practical terms, the points I pick here kind of matter. Now, any 2 points are going to describe the same line. That part is true. That doesn't matter. But we actually have to be able to draw this on our sheet of paper, and we have to be able to draw it accurately. And if we're using graph paper and a ruler, it probably doesn't matter which 2 points we're going to pick. If we're going to make our own XY axis and like try to hand draw this stuff in, it's going to be a little bit easier if we're picking points that are kind of far apart, because what that's going to do is kind of minimize how inaccurate your picture can be from like neatness error, basically. So the further we pick our points apart, maybe the more accurate of a picture we're going to get. And there's no good rule of thumb for like how far is far enough apart. So you just got to kind of take a guess. So the first value for x I'm going to pick is 0. When I plug 0 in for x, I get y is 5. And then maybe I'll pick 5 for x. When I plug 5 in for x, I get negative 5. Do the same thing over here. I'll pick 0 for x. What do I get then for y? Negative 10. And then, I don't know, I'll pick 10 for x. What do I get for y? 0. Okay. So now let's go ahead and graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'll graph the point 0, 5, and then 5, negative 5. Looks like right there. And I'll draw my line. If I wanted to do the goodest job as possible, what should I use to draw this line? A ruler. Okay. I have 0, negative 10, and then 10, 0. Now notice this system that we just graphed was the same system that I gave you guys in the example. Did you guys notice that? What did we say the solution was in the example? 5, negative 5, right? Where is that at? It's right there. Everybody agree with that? So where is the solution, or what are we looking for if we're looking for the solution when graphing? Yeah, we're looking for intersections, right? Okay. We should be specific here. So when we're solving a linear system, we get a couple of different results here. So the first one we saw in the previous example, where we get exactly one solution. Right? What else can happen? Okay, what if I have parallel lines? What's that going to mean? What was that? Somebody whispered it. No solution. Yeah, when you know the answer, shout it out loud so everybody can hear. Yep. You could have no solution. What that would look like would be parallel lines. If there's no intersections, then We can't have any solution. Now there's one more situation that can happen here. So we wouldn't say all solutions, but we would say infinitely many solutions. I usually abbreviate that phrase as IMS. What would infinitely many solutions look like? They'd be the same line. Yeah, so imagine I have this line from equation A, and then this line from equation B. We have an infinite number of intersections, because at every point on the line there's an intersection. But any point I pick, is not a solution, right? The solutions are specific, but there's infinitely many of them. I can't just slap any two numbers together and be like, oh, there's an answer. No, it's not all real numbers as the solution, or all solutions, but there's infinitely many of them. Okay. So let's make a pro-con list for graphing. So let's start with some pros. It's pretty easy to do, right? The only skill we're using is graphing a line. This was something that you guys all said when we talked in the beginning of the year was a skill you remembered from Algebra 1. Should probably feel pretty comfortable doing that sort of thing. It's visual. There's not much you need to do to get your answer after you've graphed it, right? You just need to look at the picture and interpret your result. Let's think about some of the cons, though. Well, it's a little bit time-consuming, right? If you want to draw an accurate picture, that takes a little bit of time. And maybe we should also say space. Like it takes a lot of space on your sheet of paper to draw an accurate picture. Okay. For some of us, the fact that neatness is going to count here a lot is definitely a con. I've seen some of your papers. Not everyone, but many of us, that would be an issue. What else is kind of an issue? So there's two important things here that need to go on this cons list. Two more. There could be other things that I haven't thought of yet that are definitely cons, but there's two big ones that are issues. Henry? Okay, so I would say that's probably under the neatness counts, right? If we don't draw a neat enough graph, it's going to be tough to get the correct answer out of it. But that's absolutely an issue if your line isn't straight, or if your graph isn't scaled well. That could be a problem, absolutely. But I think that kind of falls under the neatness counts category. You agree with that? Okay. So in the example, how many variables did we have in our example? 2. We had an x and a y. What would we do if we had 3 variables? You can graph in 3 dimensions, but it's not very easy to deal with because trying to put a 3-dimensional picture on a flat sheet of paper is a problem, right? What would we even try to do for 4 or 5 or 6 or 7 or 8 variables? There's not really a picture that kind of matches up with that, right? So that's an issue. So again, not a great fit for 3 or more variables. Does everybody kind of get the idea there? Like even what would that picture try to look like? There's a whole branch of mathematics, though, that is very interested in like solving big systems with lots of variables and lots of equations in them. It's a very important industrial problem. There's one more situation, or one more issue here that could be, very, very important, or very big issue. Let's go back and look at our picture that we just drew here. Now, we said the solution was 5, negative 5. What if the solution was actually 4.99, comma, negative 4.99? Is it realistic that we'd be able to look at a picture and get that much accuracy out of our picture? No. So like getting a decimal or fractional answer correct is going to be also problematic from a graph, right? Now, conceivably, you draw an accurate enough picture, and you should get that. But who in the heck has the time to draw a picture accurate enough to the hundredths place? Not me. Okay. So which side do you think wins? Looks like we have a lot of cons here, right? And some of them are pretty big cons. Like, if this situation gets much more complicated, this isn't really a very good fit. What does that tell me about this method? Probably not going to use it. I think it's an excellent introduction because you have that visual, you have a nice visual basis to look at. You have a good idea of like, interpreting that there could be exactly one solution or infinitely many or no solutions is really obvious when you're looking at it graphically, right? There's only a couple of outcomes that could occur, but to actually practically do these kinds of problems graphically is not really great. So we won't do a lot of solving graphically. You guys will do a little bit of practice with this, and we'll talk about how we can use our calculator to do this, because the calculator is immensely more precise than we're going to be able to be by hand. But we won't do a lot of solving using graphing as a by-hand method. It's not a great fit. What we'd prefer are some algebraic methods. And we'll start talking about our first algebraic method today, called substitution. So that first method I would classify as a geometric method if you're looking at the graphs or whatnot. Yeah, Ty? Of course. So I'm going to return to this same system that we've looked at now a couple of times as our example. And we're going to talk about how to solve this system by substitution. So the first thing I'm going to do is, just so that we're able to better communicate with one another, I'm going to label these two equations as equation A and equation B. I'm just doing that so we have a basis to talk about. Like if you're wanting to talk about x, which x are you talking about? Well, the one in equation A or the one in equation B. So it gives us a way to kind of describe what it is we're talking about. So the idea with substitution, right now we have two equations that have two variables. I can't solve an equation that has two variables in it, right? There's no way to get like a single answer from an equation with two variables like that. What I'm going to try to do is end up with one equation with one variable. That's my goal, is to end at one equation, one variable, because that we can solve. So I'm going to take these two equations and two variables and turn them into one equation in one variable. One way to do that is through a method called substitution. So what I'm going to do is I'm going to choose an equation and then choose a variable from that equation and get that variable by itself. Now, does it matter which equation I choose and which variable I choose? No, not in like strict mathematical terms. In practical terms, can I make this problem much harder or easier depending on my choices? Yes. And that's what I want to take a moment and talk about here. So if I look at these two equations, I see four variables. I see two x's and two y's, right? One of them would be a bad choice to try to isolate. Which one of the four would be the one we wouldn't want to choose? Which one would be a bad choice to try to isolate the variable? Hopefully you picked the 2x. Why would that be a bad choice? To get the x by itself, what am I going to have to do? Divide by 2. What's that going to create in this case? Fractions. Do I want to have to deal with fractions if I don't have to? No, I don't want to have to deal with fractions unless I absolutely have to. And there might be some problems where you have to, where there is no good choice. But here we have lots of good choices, right? Any of these variables other than the 2x would be a good one to isolate. Is everybody okay with that idea? So just for the sake of argument, let's say we picked the y in equation A. To get that y by itself, what am I going to have to do? Subtract 2x from both sides. Is everybody okay with that? That's the first step in substitution. I've isolated one of the variables in one of my equations. Well, I know that y is equal to negative 2x plus 5. So I'm going to take what y equals, and I'm going to replace it for the y in my other equation. By the way, I'm going to call y equals negative 2x plus 5 equation C. And I'm going to call this new one that we've made by substituting C into B. I'm going to call that one B. Okay, before we move on, important note here. Notice that I took equation C and I substituted that into equation B. That's good. What's bad is to take equation C and substitute it into equation A. Why is that a bad idea? Because they're the same equation still, right? What's the only difference is you added or subtracted things from both sides. They're the same equation. What's going to happen if I do that substitution? You're going to end up with 0 equals 0. All the variables are going to cancel out. Not very helpful. Okay? That one is bad. You got to substitute into the equation you haven't already manipulated. Okay. So returning down here to solve, let's go ahead and distribute our negative, and then I can combine my x and 2x to make 3x. And then I can add 5 to both sides. And then we can divide both sides by 3. And I get half of my solution, which is x equals 5. Now I still have another half to go, right? I still need to know what y equals. How can I figure out what y equals now that I know what x is? Olivia? Yeah, in fact, there's 3 places I could plug in x. I could plug it into equation A, into equation B, or into equation C. Right? There's 3 places I could plug that x in to find the y. Why can't I plug it into equation D? There's no y's in equation D, right? Oh, there's only x's. Oh, yeah. All right. Which one of these would be the easiest place to plug x into to find y? C. Why is that one a little bit easier? The y's already by itself, right? There's nothing really, there's not much left to do. So that's what I'm going to do, is I'm going to plug this into C. So that gives me y is negative 5. And the way we'll write our answers for this is we're going to write them as tuples. And the order that we write our tuple is always going to be alphabetical. So if I have x, y, z, I'd want to write my answers, my answer for x, my answer for y, my answer for z. If you had A, B, C, you'd write your answer for A, and then B, and then C. So we're always going to write our answers in alphabetical order. We have a fancy name for that in mathematics. We call that lexicographic order. I know, right? It's kind of unnecessary. Anyways, this seems like a good place to stop. We'll stop here.